Okay, I just walked through the fundamental theorem of calculus part 1. Now we're going to look at part 2, which is the focus for Tuesday's work. Here's fundamental theorem of calculus part 2. All right. This part is what you're actually going to use. I feel like this is the more practical part of the theorem, which anytime you're evaluating a definite integral, this is the theorem you use. So we're not defining a new capital F of x function here, okay? We're just looking at a definite integral from a to b of f of x dx, okay? So just the area under the curve from one boundary to the next, okay? And that's fixed. All you have to do to find that area, in this case that blue region between them, is find the antiderivative and evaluate it at b and subtract the antiderivative evaluated at a. All right? So technically the first part of the theorem allows, tells us that every function has an antiderivative, and now this part tells us that we're going to use those antiderivatives to actually evaluate a definite integral. Okay? So I'm going to show you how this works. So here's our example function. The integral from -2 to 2 of t squared minus 4 dt. Okay, so this right here is our function. That's our f of t. Okay, and we're going to evaluate this. So here's how this works. You start out by finding capital F of t, which is just the antiderivative of f of t. Okay, so you're just finding that first. And this is what we did Friday. So to do that, we say, all right, what's going to give us a derivative of t squared? Well, that's going to be t cubed. And then I got to put a 1/3 in front of that so that when I bring the power down and multiply it by the coefficient, I get a 1. And then this needs to be 4t. Okay? So you write that down, you write the antiderivative, and then the typical notation for how we evaluate this is we put this vertical bar on the end, and we put our lower boundary here and our upper boundary here. Okay? And so what we're going to do now is we're going to do the f of the upper boundary minus f of the lower boundary. Okay? That's what we're going to evaluate. And so what I do is I do equals, but I'm not going to have enough room there, so I'm going to wrap around here. 1/3 of, so yeah, start with the upper boundary first, so 2 cubed minus 4 times 2. And really I should put all that in parentheses. Then I'm going to subtract this whole thing evaluated at the lower boundary, which is 1/3 -2 cubed minus 4 times -2. Just like that. Okay, now we just got to make sure we do order of operations correctly. So 2 cubed is 8 times 1/3 is 8/3 minus 8. And then here we have -2 cubed is -8 times 1/3 is -8/3 plus 8 there. I'm going to distribute through. So I have 8/3 minus 8 plus, so I distributed the negative through to both terms. So plus 8/3 minus 8. So I have 16/3 minus 16, which comes out to be -32 thirds, which is -10 and 2/3 of a unit. Okay, I didn't write that very well. -10 and 2/3. Okay, now that's the long way. That's the process that I want you to learn, though. That's utilizing fundamental theorem of calculus part 2. I'm going to show you another example, but before I forget, I wanted to point out, please read on the online textbook, lesson 5.3, halfway down the lesson it says Fundamental Theorem of Calculus Part 2, the Evaluation Theorem. Really think it would be good for you to read through that whole thing, look at the examples there. Do that. I'm going to show you another example in a second, but what I want to do is show you how your calculator can actually do the fundamental theorem of calculus part 2 for you, or you can also use it to check. Okay, so this can evaluate definite integrals. Okay, so I don't know if you'll be able to see this very well, but I'll try. So we're going to do the same problem here, and to start with, we have to go to math, scroll down until you get to FNINT. For mine here, sorry, it's a little dusty. Number 9, FNINT. Okay, then you're going to type in the function. So in this case, x squared minus 4. I know it's t, but they use the variable x for this calculator. Then you have to do comma. Then you have to say what variable you are integrating with respect to, in this case x, comma, and then you do the boundaries, -2, comma, 2. Close your parentheses. Enter, -10 2/3. Okay, that's what we had here. Right? Use this to check. You need to show me you understand the process. Use this to check. All right, next example. I want to do a little harder one here, but I think it would be helpful to at least see another one. So here we go. Example 2. The integral from 1 to 4 of 2 minus square root t over t squared dt. Okay. All right, so here we go. First step is to find the antiderivative of that. Well, this is going to be kind of hard because we have multiple variables there. So really the first thing you guys need to do with this, you need to do some algebra, be creative with algebra, and break this fraction apart, break this subtraction apart, so it becomes the integral from 1 to 4 of 2 over t squared minus square root t over t squared. Okay, because we know there are some properties of integrals that say the integral of a function that's being like a subtraction here, where there's two terms being subtracted, you can do the integral of this and the integral of this and subtract the results. Okay, so same kind of properties as what we saw with derivatives a long ago. I just can't get comfortable here today, guys. So we're going to start with this. But before we really do much work on this, let's continue to rewrite this case being 2t to the negative second. This one here, okay, think about that's t to the negative, or sorry, t to the 1/2 on the top. And if we bring this denominator up, that would be times t to the negative second. And remember how if we're multiplying with the same base, we add up the exponents. So we have t to the negative 1/2, or t to the negative 3 over 2, right? So like I said, being able to understand that this here can be rewritten here in this way, using some algebra and some exponent rules, is going to help out a lot. Because at this point, now we go find our antiderivative. Well, what's the antiderivative of this? Well, we got to go one higher than -2, which becomes -1. What's going to give us a coefficient of 2? Well, we need a -2 here, so that when it gets multiplied by that -1 power, we're left with 2. Here, what's one higher than -3/2? Well, -1/2. What has to go here? A 2. -1/2 times 2 is going to be -1. So we got our negative, so we can just put a plus there. So once we write the antiderivative, we are evaluating that from 1 to 4. So now we use the fundamental theorem of calculus part 2. So -2, I'm going to rewrite this, guys, so that it's -2, t to the -1 is t to the first in the denominator, and so we're putting 4 there, plus 2 over, this is the square root. T to the negative 1/2 is the square root of t in the denominator. So we plug in the 4 minus, now we evaluate at 1, negative 2 over 1 plus 2 over square root of 1 there. Okay, so this is capital F evaluated at the upper boundary. This is capital F evaluated at the lower boundary. And the fundamental theorem says we need to subtract those. So here we have 1/2, negative 1/2 plus 1 minus negative 2 plus 2. Well, that's 0. Negative 1/2 plus 1 is 0.5. 0.5 is the area under that curve from 1 to 4. We have just evaluated that definite integral. Okay, let's check our calculator again. Here's the process. Math. Scroll down, or I like to scroll up because it's closer that way. Number 9. And then I got to type in the function. Now I got to be careful to get order of operations correct. So I better put another set of parentheses there. 2 minus the square root of x. Then I close the parentheses on the numerator. Divided by the x squared. Okay, now I got my whole function there. Comma tells the calculator I'm done with the function. Comma x, comma 1, comma 4. Close parentheses, enter. There it is, 0.5. That's what we got. All right, keep working away there, students. I'll look for your homework and questions in the emails.